All right, so in this video, we are going to talk about dA equals r dr d theta when it comes to polar coordinates. So why is this true? And the thing that I'm most curious about is there a geometric explanation for this? Well, let's see. Suppose we have a region in polar coordinates. That is to say, a region that looks like this. And this region, we're going to say, is bounded by delta r and an angle delta theta, where delta r is the difference between these two radii, delta theta is the difference in angle between these two lines. So then, what is the area of this thing? Well, let's say that this radius is r1, and this radius is r2. And notice that overall we have two regions. We have region 1 and region 2. So to figure out what delta A is, we can say that delta A is the area of region 1 and region 2 combined minus the area of region 1. And notice that both of these areas, that is this area and this area, are in the same exact shape. They're both in the shape of a circular sector. Now, in general, a circular sector looks something like this. If we call this the central angle, and we call this length r the radius, then the area of this thing is this. And really, all it is it's a fraction of the total area of the circle that it came from. And that fraction depends on the angle. Now, this is true as long as the angle is in radians, because this is an angle theta out of the full 2 pi radians of the entire circle. That's why this would be true. And so we're going to apply this formula to what we're doing right here. But we're going to move up to the top right here. So the area of 1 and 2 combined has an angle delta theta. And the radius of area 1 and area 2 combined is r2. So now we're subtracting this by the area of region 1, which is this region. Again, it has the same angle, delta theta. And the radius of region 1 is r1. So this is overall what we have for the area of delta A. Notice that the pi's cancel out, and so we're left with this. Now, notice both terms have a delta theta over 2, so we can factor out the delta theta over 2. And this is what we would be left with in the parentheses. But this is just a difference of perfect squares, and we can factor a difference of perfect squares. This is all it would be. So this is the area of this region. So then, what's this then? Well, this comes from the fact that we're assuming delta r becomes really small and delta theta becomes really small. So we're going to let both of these two things become really small. So if we make these two things really small, then that's going to cause this area to become really small. Right? But the most curious thing is, what happens to these two radii? Well, as delta r becomes really small, r1 doesn't have to change. But since r2 equals r1 plus delta r, well, in this case, r1 plus dr, well, dr is going to become really small compared to r1. So you can imagine delta r is going to become really small compared to r1, and therefore r2 is essentially equal to r1. And since r1 can literally be equal to anything, we could just say it's equal to some radius r. So now we're going to use this new information to re-express this, delta A, as dA. So, delta A becomes dA, delta theta becomes d theta. Now, R2 minus R1, if you were to look at this on our drawing, R2 minus R1 is delta R, which in this case, R2 minus R1 becomes dr, because that's what we're saying right here. So then, what about R2 plus R1? Well, as we've just mentioned, R2 is approximately equal to R1, so we can just essentially say it's equal to any radius R that R1 happened to be. So we're going to replace R2 and R1 both with R. So we get R plus R. Now R plus R is 2R. So this is what we get. But the 2's cancel out. And so, as you can see, we are now left with R dr d theta. And so this is geometrically where this comes from. That's exactly why this is true from a geometrical standpoint, right? That is why a really small version of this is essentially this, which is pretty cool that we can see how this works geometrically. And so yeah, this is pretty much it for this video.